So as there is no one, so let me start by sharing the screen, and you can later watch the class via YouTube link. I'll share the link. I'm recording the class and later I'll share. Okay, so let me connect with my display. Okay, so let me start with the first question. As usual, I will first write down the question and then I'll discuss the solution. You can go through this lecture in YouTube video. And if there is any doubt regarding any question, as there is nobody in the live class, so you can ask me through email or WhatsApp number I have already provided, or you can ask in the next class as well. Okay, so let me start today's class. First question is, discuss the type of discuss various types of ensemble. Okay, so this is kind of theoretical question. So ensemble we have already studied in the class, already taught ensemble. So now there are various type of ensembles, but before that let me again discuss briefly what does it mean, what does it mean by ensemble. Ensemble is basically collection, so it basically signify collection of what? Collection of, let take a system, considering a system like this. Let this is a system or container which is filled by gas. So this is a system, or you can say it is a macroscopic system, because this system is visualized by your naked eyes, so you can macroscopically identify this system. So that's why it's a macroscopic system. Okay, now if time evolves, this system will change. Macroscopically will not change. Macroscopic system, this will not change, this will not change or evolve with time. The macroscopic system will be unchanged. This container will be remains a container. The number of this is defined by n. Let's say the characteristic properties of that system, it may be temperature. We know for a macroscopic system there are some parameters, right? What are those parameters for a macroscopic system which defines a macroscopic system? That's called characteristic parameters. There are some characteristic parameters which defines a macroscopic system, just like temperature. It may be temperature, it may be pressure, it may be volume, it may be number of moles or molecules. These things, these are the macroscopic parameters which defines a macroscopic system. So now, if you take a uh, cylinder, or you take a container which is full of a gas, real gas, that will have a particular pressure, volume, and temperature, let's say, and you keep that system as it is. It will not evolve with respect to time. The number of molecule will not be changed, the pressure will not be changed, the volume will not be changed. It will be remain constant. So macroscopic system will not be evolved with time if you do not disturb it then. But if you look at the microscopic orientation of that particular system, that will change each and every time. So what I'm saying, but the microscopic picture of that system will be changed each and every time. Okay. So how you can identify, how you can think that more easily? Let's say there is a room. Okay, there is a room, and there are some sitting places. Let's say there are four sitting places. Okay, and now you uh, entered two two kids in the room. So what will be your what will be your macroscopic state? Macroscopic state will be a room having four chairs or four sitting places with kids two kids. This is fixed. If you look the overall system from outside, you will always have a closed room with four sitting chairs and two kids. That will not change. So the macroscopic system will be always four chairs plus two kids in a closed room. That will not be changed. Always it's fixed until you open the door or other things. But each and every time, you can think that each and every time coordinate of that two kids will be different. At a moment, it may be both of the kids are sitting in a same chair or same sitting places, or different, or one may be here, one may be here. Lots of arrangement you can have, right? Lots of arrangement. If you are considering only the sitting arrangement, then also there will be lots of arrangement, right? Uh, Other arrangements we can ignore for a time being, but only if you are considering the sitting arrangement, then also you will have uh, two. That means 2 to the power 4, 16 types of arrangement you will have. And if you are considering the other arrangement as well, it is always changing, always changing. So microscopic picture is always changing. So but if you want to have the uh, average value, so I think now it's clear what is a microscopic picture and what is a macroscopic picture. Now for having a average value, now coming back to these gas molecules. So we know there is a volume, there is a number, there is a pressure, temperature, these things. But now as the microscopic picture is always changing, so microscopically, we know the microscopically the overall energy is changing, volume is changing, pressure is changing. These things are changing microscopically, not macroscopically. So, but macroscopically it's fixed. So that means we have to take the average. Okay. So for that we have to do the average of any quantity x, any quantity x. Okay. This is the average of a quantity x. Okay. So this average we have to find out. This is our criteria. How we can find out? Okay. Okay, because there is nobody, so Google Meet is warning. Mhm. Okay. So now the average quantity we have to find out. So how we can find out the average quantity? Here the how the x is changing. X is changing due to change in time. So we have to calculate the time average. This is average the time average of x. So we have to calculate the time average of x because x is evolving with respect to time. Okay. So how you can calculate that x is changing with respect to time dt, let's say from 0 to t and it 0 to tau, then it's 1 by tau. This is a definition of because x is a function of t, then only it is changing with respect to time. Now if you integrate from 0 to t and it's divided by the whole time span, then it is the average quantity. So this is the original definition of the any average quantity, but it's not possible to calculate the average quantity, time average quantity rather. Okay, because it's changing each and every time it's changing. So that's why to bypass this problem, Gibbs basically introduced the concept of ensemble. Okay, so how the ensemble average is determined? Ensemble average is instead of time average. So instead of time average, we are considering the ensemble average. Instead of time average, we are considering ensemble average. This is excellent concept because calculating time average is very difficult, very difficult because we don't know how much time we have to take these things. Essentially, it should be infinity and 1 by infinity, then it's 0. So lots of difficulties are there. Again, we don't know how this x, this parameter, let's say if it is the internal energy, how the internal energy depends on time, you don't know. So it's very difficult to calculate the time average. So that's why you are considering the ensemble average. Ensemble average means, what does time average do? Time average means each and every time there is a new type of microscopic picture. This microscopic picture is essentially this microscopic picture I have written right here. This microscopic picture. This microscopic picture essentially signifies a microstate. This is essentially the microstate. And let me change the color. Okay? This is a microstate. And the macroscopic picture is macrostate. So microstate is changing always. So each and every time there is a new microstate. Means if you think like this, so if you start with let's say time 0, it's t equal to 0. After few seconds, new arrangement you will find with same number of molecules. It's t equals to 1. After 1 second, it's another type of arrangement. It's lots of arrangement that will go on. So instead of calculating these things, what Gibbs suggests that don't do it. You fix a time. Time is not now changing. He gave this concept that fix a time. Let's say t equals to 0 anytime. You took t equals to 0 at a system. Okay. Now you are not changing time. At a particular time, you make an infinite number of copies of that system with different microstate. Okay. So means that he's saying uh, now time is not changing. You are taking infinite number of copies of that macroscopic system. So Previously what happens, there was a one microscopic system and time was changing. That's why each and every time a new type of microscopic picture of that macroscopic system was generating. Now Gibbs suggests that keep the time fixed at a particular fixed time. You make an infinite number of copies of that macroscopic system. So now you have at a particular time infinite number of macroscopic system, each and every system having different microstate. That's the concept. So essentially, as you are considering the infinite number of microscopic picture of the same macrostate, so that means you are accounting all the possible time evolution of that macrostate. That is the essentially the picture. I think now it's clear. So what I am saying, okay, so means that if you considering only the sitting arrangement of particular that room, so what will have, if you consider the time average, then also you will have that 16 arrangement only. At a time there it may be arrangement two are there, other time these two are there. So what Gibbs suggests, instead of considering the time evolution of that arrangement microscopic picture, you take all possible microscopic picture, all possible. So essentially that will account the time evolution. So that's why the ensemble average and time average becomes equal. So this is an excellent concept, an excellent concept, sorry. So now you can calculate the average. How? So now the ensemble average will be the X ensemble average, that will be XJPJ. That was our definition, XJPJ, right? XJ is because now you are if it is energy, then Xj is a state, eigenstate, because now you are considering infinite number of copies of that particular macroscopic system. So there will be some energy levels, there may be some other things. So in that way you can calculate in details. We have already studied how the ensemble average is calculated, but there is a profound description to calculate the ensemble average, which was lacking in case of time average. So that's why now you can calculate the ensemble average. So this was the ensemble, but our question was what is the classification of ensemble? That's important. So basically, how the ensemble is classified, that depends upon the macroscopic system, because you are making the copies of that macroscopic system. So essentially, the ensemble types of ensemble will be depends on type of macroscopic system you are taking. Correct. So yes. So ensemble. So basically, there are three types of ensemble. Okay. First one is microscopic ensemble. Second one is ah sorry, not microscopic. What I'm right. Microcanonical ensemble. Next one is canonical ensemble. The third one is grand canonical ensemble. So essentially, there are three types of ensemble. Okay, so in detail we'll discuss in microscopic ensemble that macro state you are taking, na? So that macro state you are taking infinite number of copies of that macro state. How I'll be coming now, but first you have to understand. Just I'm going through the definition first. So here each and every macroscopic state you are taking, that each and every macroscopic state are Each and every macroscopic state are isolated. So each macroscopic states are isolated. Okay, so they are not interacting. Each and every microscopic states are isolated. That means N, V, E, all are fixed. Correct? So let me write it here. N, V, E fixed. Okay, so now in case of canonical ensemble, macroscopic systems are closed system. What was the definition of the closed system? It can exchange the energy, but not the heat, not the particle. So in this case, NV instead of T, instead of E, it's T, and T fixed. And in case of the grand canonical ensemble, macroscopic system are open. Okay, so now number of particle can also be exchanged. So as a consequences, mu Vt are fixed. So basically there are these three types of ensemble. I'm coming to that, the picture. So how the picture looks like for any ensemble. In general picture, let me draw. So it's like a collection of macroscopic system. So it's a macroscopic system. So now you have to take huge number of copies. Essentially, it should be the infinite number of copies, but for sake of convenience, I'm writing, drawing a finite number. Each should be identical. It's not happening here. Like this, and it goes on. So there are infinite number of copies. Okay, of that system. Now, essentially, for for micro canonical, for micro canonical ensemble, for micro canonical ensemble, these are called the walls, right? These are walls. Okay, wall. So these wall are, before that the systems are the system are totally isolated. Isolated means it will have fixed N, V, and E. So walls are rigid, rigid wall. Then only it will be isolated, because in between two systems, no energy will be exchanged, no volume will not exchange eventually, because volume is fixed, but no number will be exchanged. Number of molecule, now particle will be exchanged. So this is the definition of our microscopic ensemble. Clear? Walls are totally rigid. Okay. So now this is microcanonical Let me copy. Okay, so now going into canonical. In case of a canonical ensemble, these walls are not totally rigid, right? These walls are heat conducting. That's why N, V, and T is constant. N, V, T are fixed. Why T fixed? Because the concept is like that. Overall, the collection is in a thermal bath. Okay, like this thermal bath, which has a temperature T. Okay, so energy is exchanging between the systems, microscopic system, and eventually that is equilibrium with the external thermal bath, huge reservoir. So that's why eventually, ultimately, the temperature of the each and every microscopic system will be T, but the energy in that in this case will not be same. So here energy of that microscopic system vary will vary. Okay, and the systems are which kind of system? Closed system. Okay, so this is canonical. Let me again copy paste it. Hmm. So now the grand canonical. In case of grand canonical ensemble, these walls are heat conducting and as well as permeable. Now that means in between systems, now heat energy can be exchanged, also the particle can also be exchanged. So eventually N now will not be conserved. So mu will conserve, V will conserve, and T will conserve. These are fixed. So and the systems are basically open system. And the overall collection is there is a that is a thermal bath, obviously to keep the overall temperature fixed T, and also that bath is maintaining the chemical equilibrium. So this is a thermal bath maintaining chemical equilibrium. So T and mu is the so these three main ensembles are there. So if you go gradually, now from microcanonical case, it's totally isolated. Now if you just allow to system exchange the energy, then it will convert to canonical ensemble, and for that you have to put a thermal bath attached with that collection of systems, then it will be converted to canonical. Now also if you take the thermal bath which can maintain the chemical potential of that system, so then also uh, system now will be open, it will be exchanged by particle and the energy as well. So now mu Vt will be fixed and that will be a non-canonical ensemble. Okay. So these three are known, but instead of these three, there are few. There is another ensemble that is called Isobaric isothermal ensemble. So important. Okay. Isobaric isothermal ensemble. So in that case, N is fixed, pressure is fixed, and temperature is fixed. So very very important. N, P, and T are fixed in this ensemble. So this less used ensemble, but that is another one. So this is our ensemble types of ensemble. Okay. Now going to the second question. Even I will write the question first, then we will discuss. Okay. Mhm. Derive the forms of vibrational partition function at high temperature limit and low temperature limit, considering theta equals to h nu by kb. Okay. So what was the partition function? Okay. And now if you put theta equals to h nu by kbt, not kbt, it's kb, or theta v equivalent. Now I'm just using theta because there is no rotational partition function, so there is no chance to be confused. So you can write it. So this is our QV, vibrational partition function. We know. Now we have to evaluate the forms of the vibrational partition function in higher temperature limit and lower temperature limit. Okay. For that, let theta by 2t is x. Suppose. Hence, e to the power minus theta by 2t mentioned here. What will be the form e to the power minus theta by 2t? So it will be e to the power minus x. And we know the exponential series, right? E to the power x is 1 plus uh, x plus x square by 2 factorial plus x cube by 3 factorial plus and so on. So what will be for e to the power minus x? Just these things. Just you have to put minus x instead of x. So and so on. Okay. So now they are considering the high temperature limit. Okay. Okay. Let me write it here. Now, as the temperature is high, so we can say this parameter x tends to 0 because temperature is very high. X is not very small, rather. So if x is very small, so we can only considering the linear term 1 minus x, neglecting the higher order term. Okay, so we can write. So it will be 1 minus theta by 2t. Okay, and this is case. So this is our numerator. Now in case of denominator, that we have to now find out, that is 1 minus theta by t. Okay, so again, if it is 1 minus theta by t, so what we can write is 1 minus theta by t. Now again we have to approximate. It will be this part. Let's say this is essentially we can write 1 minus theta by t using the same formula. Using the same formula, we can write it because here also t large. So 1 minus theta by t will be, this will be 1 minus this. So it will be theta by t only. So now you can write. So what you can write now? That q vibrational will be 1 minus e to the power theta by 2t divided by 1 minus e to the power minus theta by t. It will be 1 minus theta by 2t divided by theta by t. Correct? So if you take the log LCM, it will be 2t into t by theta. So t will be cancelled out. So it will be 2t minus theta by 2 theta. So it will be t by theta minus half. Okay. So t by theta. So t by theta. What is theta? Theta is h nu by kb. So it will be kbt by h nu. So it will be kbt by h nu divided by half. Okay. So q vibrational will be kbt by h nu minus I not divided minus half. So this is our at higher temperature limit. Clear? So again you can ignore the half, but still not necessarily. Okay. Now we have to calculate in case of lower temperature limit. Low temperature limit, let's. So again we know qv that is fixed. E to the power minus theta by 2t divided by 1 minus e to the power minus theta by t. This is correct, we know. Now you have to consider the in case of lower temperature. In case of lower temperatures is theta by t. This is important, right? Let's say what we've done, that t was very large, so theta by t was very big. Here theta by t is very large, right? Why theta by t is very large? Because t is very small, low temperature limit, so t is very small, so that's why theta by t is very large. Okay, so now let me do other way. So what we can do here, e to the power theta by t, this we have to look at it. So this is, if t is very low, so theta by t is very high, so this will be very low. E to the power minus theta by t is very minus theta by t is very low. So in that case, you just put, if it is 0, let's say if it is 0, then it will be e to the power theta by t to the power theta by t. It's 1 by 0. So you can ignore this term essentially. So this term can be ignored. Okay. So if you ignore this term, let me do in another way. It's not a correct way to do it. Essentially, it is this. Okay. Because you can ignore this term. I'm just finding a valid logic to do this. You can understand that because theta is low, but here 2 theta is there. So you can ignore this part and can consider this part as well. But this is not a correct argument, I think so. This is correct. What we can say here. Okay. For time being, let let me think about this question, about this problem. How to approach this problem. I will discuss later, probably in this class at the last or next class. So this is a valid question. Okay, I will do it. I'll do it. Okay. So okay. So now going to the question number 3. For H2 gas at 3000 Kelvin, what is the vibrational temperature which is written as theta vibrational and vibrational partition function which is written as Q vibrational respectively. Given that the fundamental vibrational frequency of this, so we have to find out Q vibrational and theta vibrational. What is given here? Given the fundamental frequency means nu is given, that is centimeter inverse. So eventually this is nu bar. We know na that E equals to h nu, we know. So and we know the nu lambda equals to c. Okay, and nu bar, that is the wave number, not the frequency. This is actually the wave number defined as 1 by lambda. So from here you can write lambda equals to c by nu. So 1 by lambda will be nu by c. So wave number is actually nu by c. That's why it has unit of centimeter inverse, because nu has unit of second inverse and it is, let's say, centimeter second inverse or meter second inverse. So it will be centimeter inverse. So this is our nu inverse. So we have to find out now theta vibrational. Okay. So theta vibrational will be, we know h nu by kb, and now nu equals to c nu bar. So just c nu bar h by kb. Now we have to put 3 into 10 to the power 10 centimeter second inverse. New bar is 4405.3 centimeter inverse, and h 6.626 into 10 to the power minus 34 joule second. Now what is kb? 1.38 into 10 to the power minus 23. And what will be the unit? What will be the unit? What is the unit of kb, let's say? Because kbt is unit of joule, so kb should joule Kelvin inverse. Okay. So now if you put it, so unit you can check, centimeter goes away, second goes away, joule goes away, so Kelvin. It should become, because essentially it's called the vibrational temperature. Unit of temperature it has. So now we have to calculate this. Where is my calculator? So it's 3 into 4405.3 into 6.626 divided by 1.38. So it's a huge number. Okay. Oh, so it's 6 point, not 6 point, it's actually 6344455.47 into 10 to the power 10 34 23. So it's actually 10 to the minus 24 and 10 to the power minus 1 Kelvin. So it's 6345.547 Kelvin. Okay, approximately this is the value. Now next is Q vibrational. What is Q vibrational? Okay, here you can think that this temperature is very high, but you have to keep in mind that don't use that, because for I'm saying, yes, 3000 Kelvin is very high, but you have to keep in mind that theta by T, where we have derived this part here, high temperature limit, what does it mean? You have to understand the science. This is theta is very, very less than T. T is very, very higher than theta. Then only you can approximate this, now. Otherwise you can't. Okay. So here theta is eventually very big. So you can't do that. You can't do that. You have to calculate. So Q vibrational will be e to the power minus 1 minus e to the power theta by. This formula you have to take. So now it is e to the power minus. Just you have to do now the numerical calculation, and you can do this. Okay, let me do. Okay, what is theta by 2 t? Theta by 5.54 divided by 2 divided by 3000. So it's 1.05. So it is 0.05 divided by 1 minus, so it is 2.115. Yes, minus sign is there. So now if you put it, so this denominator is 1 minus this, and the numerator will be 0.349. Okay, so it is 1 minus It's eventually 0.3968. So this is our partition function. Okay. I think there is no mistake. Okay. Now going to the next question, question number 4. The molecular partition function of a system is given by so essentially this is a translational partition function you can identify by the form. Okay. Okay. So this is given, molecular partition function is given. Now you have to find out the heat capacity. Okay. So what was the definition of heat capacity? At constant volume means CV, that is del U del T heat. Okay. From thermodynamics we know, and U is actually the E average. Statistically, if you want to say, and E we know how we can find out the E average. E average is basically KB T square ln, sorry, dln Q by dt at constant volume. Okay, so this is our formula. Q is known. Q is known. So here this is now small q because it's given. Just we have to do it now. Okay. So let me write what is Qt function temperature. 3/2. Okay. So you can write 8 y square m kb square by h cube c to the power 3/2 and q. We can write it. No, no, no. C must be there. Is there C? Yes, there is C. So C must be there. Okay. This is our ln dq. So now consider the ln q. So ln q will be, you have to just take the ln. So it is partition function should be unitless, right? So kbt. So what will be the unit? kbt h squared m. This 8 pi square m kbt, this form is related to the rotational partition function, right? And this, so this is our overall form. This must be unitless. So let me check the unit. Okay, let me check first. Mass is there, so it's kg. Kb is joule. Kb has unit. Square divided by h joule per second. Not joule per second, joule second. C. This is meter per second. So 3 by 2. So it will be kg divided by meter joule second square divided by 3 by 2 and Kelvin to the power minus 3. So Kelvin goes away. Okay. So this should be unitless. So kg. What is joule? Joule is Newton meter. Newton is kg into meter per second square into second square. Excellent. Yes, so this is unitless. Excellent. It's correct. Okay, so let us proceed now. It's correct. Plus 3 lnt. Now dlnq dt. So this part, in this part there is no t, right? So this part will be 0. So here this will be 3 ddt of ln t. So it is 3 by t. Okay. So now daily, not daily, average E will be kbt square dln q dt. So it will be now kbt square into 3 by t. So it is 3 kbt. So if it is 3 kbt, so cv will be, so it's essentially the u. It is del u del t v. So it is del 3 kbt del t v. So it is 3 kb. Okay, this is cv. Now if you want to calculate this for 1 mole, so essentially cv bar will be NaCv. So that will be 3 kb Na. So this is known to us, that is 3. Okay, clear. Okay, so now question number 5. The vibrational partition function for a molecule. Before that, let me drink some water. The vibrational partition function for a molecule which can be described as a so they are asking that vibrational partition function which is described by C field harmony oscillator fundamental frequency is also known, so they want to they asked to calculate the vibrational partition function. Okay. Okay, this we know actually, right? This is our just derivation of the partition function. Yes, nothing is there. So this is not a question even. This is just the derivation. So this is already discussed in class, so I'm skipping this question. Okay, so let me do that. Yes. The molecular partition function for a system in which the energy levels are equispaced by epsilon. Okay, so molecular function partition function we have to recognize. For which the energy levels are equispaced by epsilon and options are given. This force. Okay, so how we can do? We know the partition function Q, how it is defined. Or let's say J. So this is our definition of partition function. So here energy levels are equispaced by epsilon. So it is actually to the power minus, if you start with 0 to infinity, then you can write it's 1 plus e to the power minus beta epsilon plus e to the power minus beta epsilon. This will be 1, this will be 2, 3, so on. Let's say it's to be consistent and so on. This is okay. So equiphase. So let us start level from 0. So after that it will be epsilon, after that 2 epsilon, after that 3 epsilon, and so on as they have asked. So it will be 1 e to the power minus beta epsilon, e to the power minus 2 beta epsilon, e to the power minus 3 beta epsilon, and so on. Now, if you take consider, not take common, let consider e to the power beta epsilon is x. So you can write it and so on. So it is actually 1 by 1 minus x when x is less than 1. So it's correct because x is here actually e to the power minus beta epsilon. So it's less than 1 because it is actually 1 by e to the power beta epsilon. So beta is positive, epsilon is positive. So this is actually less than 1. Okay. So in that case, you can write it epsilon. So it should be option E. Okay. Now question number 6. What is vibrational contribution? What is the vibrational contribution to the molar heat capacity of it's probably not this section, right? Yes. Okay. N2 gas at 1000 Kelvin, the vibrational temperature. So we have to find out the vibrational contribution to molar heat capacity. Okay. So how we can do that? Let us do. CV is del U del T V, and U is essentially the daily average. So del is kBT square dln del T at V. Correct. So just for vibrational contribution, that means this Q should be Q vibrational. So now you know the Q vibrational is eventually e to the power theta by 2p 1 minus e to the power theta by 2. Theta is the vibrational temperature and T is the temperature. So here theta by T is eventually, can write 3374 divided by 1000. This is a unitless quantity. So it is eventually 3.374, and theta by 2t, that would be half of this. So what is the value? 3.374 divided by 2, 1.687. So QV will be, but it is not needed even though. No, it's not needed. Okay, this is important. Okay. But now we have to first find out CV. So let us do carefully. What will be ln QV? It will be ln of this quantity. So ln a by ln of ln of a by b means ln a minus ln b. Correct. So it will be theta by 2t minus 1. So ln cube is theta by 2t minus 1. So dln cube v by dt. So only this term will survive. So it will be theta by 2t square but minus. If I'm not wrong. Is there any minus sign? Probably there is a minus sign, right? Here, what is the form of? Yeah, but it's correct. So yeah, but it is essentially yes, it's correct. Okay, what I have done here. Okay. So it will be the case. So theta by 2t. So now from the first term it will be minus theta by 2t square and 1 minus will goes away. So this will be theta by 2t square and minus del t of ln 1 minus e to the power minus theta by t. So it will be theta by 2t square minus this will be, let's say this is z. So it is del z of ln z into del z of del t. So it is theta by 2t squared minus 1 by z, and it is del t of z. Z is actually 1 minus e to the power minus theta by t. Correct. So it is theta by 2t squared minus 1 by z, and it will be minus ddt of e to the power minus theta by t. So let me do it. Del t of this one. So you can write it 1 by minus minus will be plus, and del 1 by z. Z is eventually this factor 1 minus e to the power theta by t into del t of e to the power minus theta by t. So del t of e to the power minus theta by t. So it will be, let's say, x e to the power x into del x del t. Correct. So e to the power x will be e to the power x, and ddx will be, this will be del t of minus theta by t. So e to the power x, theta will be constant, theta is there. So it is del t of 1 by t. So theta to the power x, it is 1 by t squared. Minus will be goes away. So you can write it theta to t squared plus theta e to the power x. What is x eventually? X means minus theta by t. So it is minus theta by t divided by t square into 1 minus e to the power minus theta by t. Okay. So again you can simplify this as theta by 2t square plus theta by t square e to the power theta by t minus 1. Correct. So again you can simplify, not necessarily, let me stay here. So this is our dl and dt. So what will be daily, not daily, the average energy, that is kb t square dl and q by del t at constant volume. So it is actually kb t square into theta by 2t square plus theta by t square into e to the power theta by t minus 1. So it is kb theta by 2 plus kb theta by e to the power theta by t minus 1. So this is our E average. This is actually our E average, means internal energy. So it is eventually the U. So Cv will be del U del T at constant V. So this term will be 0 because there is no T. So it will be essentially kb theta del T of 1 by e to the power theta by T minus 1. So this again we have to do. So let us do like this. V theta, again let's say it's y. So it is 1 by y into del t of y. So it is kb theta minus 1 by y square into del, this is del t of e to the power theta by t minus 1. So it is minus kb theta. What is y? Y is this term e to the power theta t minus 1. So e to the power theta t minus 1 square, and it will be, again a minus sign is coming, right? No, then it's correct. Okay, let me do. So it is del t to the power theta by t minus 1. So it will be del t of e to the power theta by t eventually. So del t of e to the power theta by t. It is already done, now it's minus. Okay, so this term again you have to evaluate. So for this term, let's say u, e to the power u, so e to the power u will come out and it is del t of theta by t. So it is like this and it is minus 1 by t square and theta will be there. So it is, so you can write it. So minus will be goes away, kb theta e to the power theta by t is 1 square and this is e to the power theta by t into theta by t square. Okay, so it will be kb theta square e to the power theta by t divided by t square into to the power theta by t minus 1 square. So this is the form. This is the form of CV. It's very, very important. If you remember this form, then it is very easy. But if you don't remember it, then it's difficult. So this is the form. Okay. Okay. If you remember, then you can directly apply. So this is our CV. So just now we know the theta was given 3374 Kelvin and T is 1000 Kelvin. Correct. So now you can write it. So now theta by T. So let's say theta by T is 5. So it's eventually 3.374. It's a dimensionless quantity. So you can write it, it's like kb 5 square e to the power 5 divided by e to the power 5 minus 1 square. Correct. So now we have to calculate what is e to the power 3.374. It is 29.195 divided by minus 1, 28.19 and square it. So it's eventually 794.962. And here is kb. Okay, this is CV. But now if you want to calculate CV bar, then it will be NAKB, and NAKB is eventually the R. Okay, so R, and R we know 8.314 in Joule. Let me do 314. R, this is eventually the R. Phi is unitless, so eventually overall the unit will come from the R, which is Joule, Kelvin inverse, mole inverse. This is okay, but still phi squared is there. Phi square is 3.374 square, so it's actually 11.383. So now we have to do it. So into 8.314 into 29.195 divided by 794.96. So it's coming 3.4758 joule Kelvin inverse mole inverse. Okay. So this is the overall solution. So it's a lengthy solution because we have to derive this CV contribution, vibrational contribution to the molar heat capacity. Okay. So going to the next question, question number 7. So here again, they have asked, what is the fraction of N2, again N2 gas. molecules in the V equal to 0 and V equals to 1 vibrational states at 300 Kelvin. Okay, so we know what is the fraction. Fraction at any V will be the number of that V and total number, that means sum over NV. It is the fraction, right? It's the fraction. Eventually, this is the population. This is the probability, right? Probability of finding. We know this is the definition of probability, and we know we can write how the probability was defined. The probability is basically the e to the power minus beta epsilon j divided by sum over e to the power minus beta epsilon j, and denominator is eventually the our partition function q, that we have to just consider here. So what will be the q? So again here q will be just two levels are given, so just we are considering the first level and the second level. These two levels we are just considering. Okay, no, theta vibration of n2 is given, right? Acha, theta vibration of n2 is given here. Additionally, one information is there that I have not mentioned. Additionally, theta vibration of n2 that is given is 3374 Kelvin. If theta vibration is given, okay, then you can calculate q explicitly. What will be the q? Q will be to the power minus theta by 2t divided by 1 minus e to the power theta by t. So theta by 2t will be 3374 divided by 2 into this is this will be 3374 divided by 600, so it's 5.623. Similarly, theta by t will be 4 divided by 300, so 11.246. So if you write, then q will be e to the power minus 5.623 divided by 1 minus e to the power 11.246. Okay, so what will be the case then? E to the power minus 5.623, it is 0.00361 divided by e to the power minus 11.246. So now 1 minus e to the power minus 11.246. So it is 0.9999 something. Okay, so if you calculate q, then it will be 0.00361 divided by 0.999 and so on. So it is eventually 0.00361. So q is there. So f1, f0 will be e to the power minus beta epsilon 0 divided by q. So e to the power minus, what will be the beta? Beta eventually is the kVt, 1 by kVt. So it is epsilon 0. Epsilon 0 is known or not? What will be epsilon 0? Hmm. Let me do. Epsilon 0 is not known, right? Then how should I approach? Minus theta. Yes, this is the definition. If epsilon 0, epsilon 0 and 1. Okay. Q is known now. Q is known. Q is this. And this is our general definition of partition function. Okay. Oh, this is vibrational states, right? Vibrational states, that's given. So in case of vibrational states, we have to find out. There are two ways. You can directly put epsilon equal to 0, but that is not correct. Because epsilon equals to, for vibrational state, we know this is half h nu. In general, let me write it. In general, h nu, e nu equals to, not nu, half. V plus ev equals to v plus half h nu. This is nu. This is v is the quantum number. So from here, e0 will be half h nu. Okay. So now beta epsilon naught will be half of beta h nu, right? So now we know theta. Theta is eventually h nu by kb, correct? So you can write it half h nu by, this is kbt, because beta is 1 by kbt. So you can write it half of theta by t. So it's eventually theta by 2t. That's the case. And this is known. So f0 will be e to the power minus theta by 2t divided by q. So e to the power minus theta by 2t, we know theta by 2t was this. So it will be e to the power this. So 0.0036137 divided by 0.00361. So it's more or less equals to 1. Okay, f0, and f1 will be this. So beta epsilon 1 will be beta 3 by 2 kbt, 3 by 2 h nu, sorry. So it is 3 by 2. What is h? This h nu by kbt again. So 3 by 2 theta by t. So 3 into theta by 2t. So it will be e to the power minus 3 into theta by 2t divided by q. So it is, what is theta by 2t? 5 point. So e to the power minus 3 into 5.626. So it's 4.6 into 10 to the power minus 8. So it is 4.67 into 10 to the power minus 8. It is 0.00361. Okay, so it's coming 0.00040 are there. It's 1, 2. So it's 1.2 into 10 to the power minus 5. So eventually it's close to 0. Okay, so this is f0 and f1. Now the question number 8. What is the vibrational partition function for bromine at 300 Kelvin If the vibrational frequency is 151.2 centimeter inverse, it's also straightforward. I'm not doing this calculation again because you know what will be the partition function. Q vibrational is e to the power minus theta by 2t divided by 1 minus e to the power minus theta by t. Just t is given, theta is given, so just what you have to do, not theta is not given, theta is not given, theta is h nu by kb. So nu is given, h you know, kb you know. If it's just a numerical exercise, you can do this. So going to some different question. Okay. Could I do this? Okay, let me do. How much time? Okay, so theta will be h, you know, 6.626 10 to the power minus 34. Nu is given, again, it's again in terms of centimeter inverse, so you have to use this formula. So let me calculate theta first. So theta will be centimeter. So it's 151.2 into 3 into 10 to the power 10 and divided by what is kb? This is kb. So if you calculate it, it will be 6.626 into 151.2 into 3. This it is. This is theta. So just now you have to put it. And what is T? 300 Kelvin. So theta by T will be 0.725 and theta by 2T will be 0.362. So QV will be e to the power minus 0.362 divided by 1 minus e to the power minus 0.725. So it will be 1 minus 0.4843. Okay, so it is 1.351. Okay, this is our vibrational partition function. So now going to question number 9. Okay, the temperature dependence of partition functions. Okay, okay. No, this question is difficult. Different question, so let me check. Yes. Okay. What is the question? A molecule has a ground state and to excited electronic energy levels all of which are non-degenerate with the energies and it too is okay if P2 are the fractions of molecules occupied in the ground first and second excited state, then P0 is to P1 is to P2. Okay, so energies are known. Just we have to find out the again the fractions we have to find out here. Okay, and the ratio. So what will be P0? Q will be this. Similarly for P1 it is this. Okay, so the Q will be goes away. Okay, so epsilon 0 is 0, so it will be 1. Okay, like this. Now we have to calculate what is the beta. Beta is known. Beta is known, obviously. What is beta epsilon? This is eventually epsilon by kbt, and epsilon is this one. Okay, okay, we are taking here this is equivalent to epsilon, so it will be 3 epsilon, not 3 epsilon. Okay, okay, no, you can't use this we have to calculate separately. Now beta epsilon 1 is equal to epsilon 1 by kbt. Epsilon 1 is that is kb, and t is 293. Okay, so it will be 0.0024 into 10 to the power 3. So it's 2.431 even. So e to the power minus beta epsilon 1 will be this 0.0879. No, it's 0. E0 is 0. So if you put 0 here, so eventually it will be 1. Now again beta epsilon 2. My fault. It's not. It's even given 20. So you can directly write. It's actually 3 epsilon 1. So it will be 2.433. This. So ratio will be direct I'm writing 1 is to this is the ratio. Okay, and it should be okay. So let me check whether any question left or not. Okay, so let me do the last question. It is 10th question from rotational partition function. The rotational partition function of a diatomic molecule with energy levels corresponding to okay. So this we have to calculate the partition function. Energy levels is given for 0 and 1, and epsilon is constant. That is also provided. Okay. So what will be the partition function? This is partition function is correct till that it's correct up to okay for non-degenerate case. Okay, here if there is degeneracy, then the general formula of partition function is eventually this. You have to safely use this because there may be degeneracy because it's a rotational part level. So in case of rotational energy states, there is a degeneracy. For rotational case, degeneracy is actually 2j plus 1. Degeneracy at the jth level. So for rotational partition function, it will be 2j plus 1 into to the power minus beta epsilon j. Okay, and epsilon j, there is a form, the energy of rotational partition function. Uh, what was the form of the rotational energy? Let me check once. Yes, so it's actually bj into j plus 1. This is the energy. Okay. Mm, now, if you put here only two levels are there, right? Only two levels, 0 and 1. So it will be, for 0, it is just e to the power minus. If you put 0, obviously E0 will be 0. It's always 0. So you should not carry. Uh, so it's 1. And for second case, it will be obviously 3 e to the power minus beta epsilon 1. And epsilon 1 is eventually 2b. So it will be 1 plus 3 into e to the power 2 beta b. And beta is kbt. So 2b by kbt. So b by kbt, we consider this as epsilon because b has a form. B is a constant here. It is B. B is actually B is actually H by 8 pi square IC. Okay. So if you write it, so it will be 3 into to the power minus 2 epsilon. So it's eventually option B. Okay. So let me stop here. Okay, as there is no participant live class, so eventually there is no question. So let me stop sharing. Okay, now I will share the lecture video, share the link after uploading in YouTube, and also I'll share the notes of today's class. Please go through it, and if there is any doubt, you can ask me in the next class, or you can also directly contact with me through WhatsApp or mail. Okay, so let me stop here for today. Thank you for attending.